Hello and welcome to this video. So in this video we will solve 21st set of problems. Uh, you need to watch till the end of the video to see how you can get the PDF of this. Or I have already told in one of the videos, you can visit my website astavakra.org. You can download from there. I'll show that at the end of video. So as always, I will say that when I am stating the problem, you should pause the video. And if you cannot solve a problem yourself, then look at the solution. So question 201 says that, is it possible to find three quadratic polynomials f of x, g of x and h of x such that the equation f of g of h of x has 8 roots 1, 2, 3, 4, 5, 6, 7, 8. So we look at the function capital F of x is equal to f of g of h of x is equal to, it will be x minus 1, x minus 2 into x minus 3 up to x minus 8, which we have written as the product of x minus I, where I varies from 1 to 8. Now we differentiate it once and we find that the derivative is 4 into 2x minus 9 into x to the power 6 minus 27 x to the power 5 plus 288 x to the power 4 minus 1539 x cube plus 4299 x square minus 5886 x plus 3044. Now we see that the 6th degree equation is irreducible, but f dash x is f dash of g of h of x into g dash of h of x into h dash of x, which is not possible. Hence the required condition is not possible. You see, f dash x, when you try to resolve, you'll get three linear functions. There are three of these. One is f dash x, one is g dash x. Not linear, I mean polynomials are there, g dash and h dash. But here we got only two. So can't be. Now question 202 says that let p of z is equal to az cube plus bz square plus cz plus d, where a, b, c, d are complex numbers such that their modulus are 1. Basically it's unit circle on Argand plane. Okay. Show that p of z greater than or equal to square root of 6 for at least one complex number z satisfying mod z is equal to 1. Now we let, if we have been given that mod of a, b, c, d are 1, so we let mod of z is equal to 1. Then that will imply that z bar is equal to 1, which means z bar is equal to 1 by z. And we know that mod of p of z squared is equal to p of z into p of z bar. So we expand this and we get mod of pz whole square is equal to 4 plus 2 of real of ab bar z plus az bar z square plus ac bar z cube plus bc bar z plus bd bar z square plus cd bar z. So this is what we obtain for mod of pz square. The real part is taken, imaginary is discarded, because modulus will not have the imaginary part. Now let omega is equal to e to the power 2 pi I by 3 as third root of unity. Then you will find that mod of pz whole square plus mod of pz omega whole square plus mod of pz omega square whole square is equal to 12 plus 6a d bar z cube. So we can choose a z0 such that a d bar z0 cube is equal to 1. Then one of the terms on the left must be greater than or equal to 6. So why this should be greater than or equal to 6? So you see, if this is 1, then it becomes 6 plus 12, 18. So suppose there are three numbers x plus y plus z is equal to 18. Okay, rather x square plus y square plus z square is equal to 18. So the equality will be established only if, or in other words, you consider that x square plus y square plus z square greater than or equal to 18. Then the condition for establishing equality is that one of them must be equal to 6. For other values, it would be greater than what you call um, 18. Now you also observe that the minimum value of this pz bar square is equal to 4, because the maximum value of this can be 0. The minimum value is also there to be considered. So 4 plus 4 plus 4 will be 12, and this 12 will cancel out. So maximum is value for this is square root of 6. So that's what is being asked, that mod of pz should be greater than or equal to 6. Consider question number 203. Consider two monic polynomials f of x and g of x of degree 4 and 2 respectively over real numbers. Let there be an interval a b of length more than 2 such that both f of x and g of x are negative for x in a comma b, and both are positive for x less than a and x greater than b. Okay, so you observe that for less than a, it is positive. So consider xy axis, you take an a, so it is positive for x less than a. So when you go towards left side, it is positive above x-axis. And between a, b, both would be negative below a, b, below x-axis. And again for x greater than b, we have positive. So you see, both f of x and g of x should cut the x-axis at a and b. Okay, there is no other way we can have this condition. Now we have to prove that there is a real number alpha such that f of alpha less than or equal to g of alpha. So we let a and b be the roots. We have the fact that a, b are roots of fx and gx. Now these are monic polynomials. Okay. So first we assume that they repeat evenly for f of x. That is, a occurs twice for f and twice for b. And for g, they are one time. So it occurs evenly. Okay. Now, since these are monic polynomials, we can write that alpha minus a whole square into alpha minus b whole square is equal to alpha minus a into alpha minus b. So we have alpha minus a into alpha minus b into alpha minus a into alpha minus b minus 1 less than or equal to 0. We substitute alpha is equal to b plus c. So it becomes 2 plus c into c multiplied with 2 plus c into c minus 1. So c into, okay, let's hang on for a bit. We substitute b plus c. So this becomes b plus c minus a. And this becomes c. So what is given? Okay. So the length is more than 2. That is, b minus a is 2. So that is where that 2 is coming from. So now once we have this, we can write this as c into c cube plus 4c square plus 3c plus minus 2 less than or equal to 0, which is true for very small c. Okay. So when c is very small, this quantity would be less than 2. Otherwise, what will happen is, if it grows, then c will be positive and this will be what you call negative. Okay. So that's how we arrive at that. Now we let a has multiplicity of 3 and b has of 1. Then we need to prove that x minus a whole cube into x minus b less than or equal to x minus a into x minus b. And we proceed in the similar fashion, and we find that this is true because b minus a greater than 2. Okay. Let's move on to next problem. Question 204 says that let P1 of x is equal to x square minus 2 and Pj of x is equal to P1 of Pi of x, where I is equal to 1 to 3 and so on up to n possibly. Show that for any positive integer n, the roots of the equation Pn of x is equal to x are real and distinct. So what we do is we try to put something like x is equal to 2 cos t. Okay. So the values will oscillate between minus 2 and t 2. Okay. All right. So once we have x is equal to 2 cos t, we find that Pn of x is equal to 2 cos 2 to the power n t. And Pn of x is equal to x, which is given, implies that cos 2 to the power n t is equal to cos t, which has 2 to the power n solutions, giving 2 to the power n distinct solutions in x. Now question 205 says that find all polynomials f satisfying f of x square plus f of x plus f of x plus 1 is equal to 0 for x in a set of complex numbers. So observing the given relation which we need to establish, if alpha is a root, then alpha square is also a root. Similarly, if alpha minus 1 is a root, then alpha minus 1 whole square is also a root. If mod of z greater than 1, then it implies that there are infinitely many roots. And if alpha is in the set minus 1 to 0, or alpha is in the set 0 to 1, it implies that there are infinitely many roots. Thus, fx can have only 0 and 1 as roots. Okay, because it cannot have infinitely many roots. We also see that if we have one root of one kind, then it must also have the root of the other kind. So what f of x would become is kx to the power a into x minus 1 to the power b, where k is not equal to 0. Now using the identity, we get that minus k is equal to x to the power a minus b into x plus 1 to the power b minus a, but k is a constant. Hence a is equal to b and k is equal to minus 1, and thus minus x to the power n into x minus 1 to the power n is one form of function. Now we see that complex numbers which are root of unity and satisfy the property z1 is equal to z2 square will also be roots of this identity. For example, cube roots of unity, deducing similarly, we find that minus x square plus x plus 1 to the power n is another form of the function. If f of x is equal to c, then c is equal to minus 1 or c is equal to 0 will also satisfy this. So we now solve question number 206. Find all polynomials p of x for which p of x into p of 2x square is equal to p of 2x cube plus x. Now p of 2x square is equal to p of 2x cube plus x by p of x is an even function, so that either both p2x cube plus x and px are even functions or both are odd functions. That much we can observe by looking at the given relationship, because left hand side is even, so this should also be even. We also see that p of 0 into p of 0 is equal to p of 0. So once we have that, we establish that p of 0 is equal to either 0 or 1. Now if p of 0 is equal to 0 and px is even, let a 2n x to the power 2n be minimum power of x. And then what we have is p dash of x plus a 2n x to the power 2n into p dash 2x square plus a 2n 2x square to the power 2n is equal to p dash 2x cube plus x plus a 2n into 2x cube plus x to the power 2n. Once we have that, we consider only lower powers of x and we find that a 2n is equal to 0. Similarly, we find that for p of 0 is equal to 0 and px is equal to odd, we can prove that px cannot also be odd. So that is what you need to prove. I will let you fill the gap. If you have questions, let me know in the comments. So p of 0 is equal to 1 and px is even, then p of x is equal to 1 plus sigma k is equal to 1 to n a to n x to the power 2n, where a to n would be 0. Now putting 1 to n, we find that p of x is equal to 1 plus x square to the power n. Now we have the next problem. Find all polynomials f of x such that f of x into f of x plus 1 is equal to f of x square plus x plus 1. Now if fx is a constant k, then k square is equal to k. So you substitute in this, it will become k square and it will become k. So f of x will be either 0 or 1. But we again consider the given identity, we set x is equal to minus 1. So what we will have is, we set x is equal to x minus 1. We will have f of x. So f of x plus 1 will become f of x. And f of x will become x minus 1. And right hand side will become f of x square minus x plus 1. Now we consider fx is not a constant. Assume that we have one complex root. Let z be at maximum distance from O. So from our equations, f of z square plus z plus 1 is equal to f of z square minus z plus 1, which will be 0. Thus z is not equal to 0. Also z square plus 1, if also z square plus 1 not equal to 0, then z square plus z plus 1, z square minus z plus 1 and minus z are vertices of a parallelogram. Thus either of z square plus z plus 1 or z square minus z plus 1 is greater than mod z, which is a contradiction with the choice of our z, because we chose z to be at maximum distance from O. Therefore other vertices cannot be at greater distance. Thus we conclude that z square plus 1 is a factor of f. Hence f of x will become x square plus 1 to the power m g of x, where m is in the set of natural numbers and x square plus 1 does not divide zx. Putting this in equation, we see that it is satisfied. We also see that g of x satisfies our equation. Since it is not divisible by x square plus 1, therefore gx must be 1. Thus we have the solution as f of x is equal to x square plus 1 to the power m, where m is in the set of natural numbers. Question 208 says that find all polynomials f of x such that f of x into f of minus x is equal to f of x square. One thing I'll say that these problems are somewhat difficult, or rather quite difficult, and that is also one of the reasons why I'm not explaining completely. Okay, for example, you look at these three problems, or even in this problem, or in this one was easy. So consider problems from 203 to 208. Okay, you need to do something that extra which I talk about. You need to put something from your side. For example, here we put x is equal to 2 cos t, and here we put z plus 1 and all that. We assume that z is at maximum distance and such addition from our own side to solve the problem. So that is why it makes the problems difficult. But once you solve all such problems, okay, you develop an intuition for solving another problem which you are not seeing yet. Okay, so that's the entire objective of doing these problems, is that you develop the intuition for solving such difficult problems. Now question 208 says that find all polynomial f of x such that f of x into f of minus x is equal to f of x square. So we see that alpha is the root, then alpha square is also a root. Thus mod of z greater than equal to 1, greater than 1, or 0, mod of alpha lies between 0 and 1. That is essentially mod of alpha is not equal to 1. So there will be infinitely many roots in these cases. Therefore all roots must lie on the unit circle. Now fx is a constant, then c square minus c square is equal to 0. So c is either 0 or c is 1. Let's assume that f of x is equal to x plus b, then x plus b into b minus x is equal to x square plus b, which gives a is equal to minus 1 and b is equal to 0, or b is equal to 1. So we see that f of x is equal to minus x and f of x is equal to 1 minus x. So we get this. Now we consider f of x is equal to x square plus bx plus c, and we repeat the same exercise. We substitute in the given identity and we solve. And if c is 0, then b is equal to 0 minus 1, And if c is 1, then b is 1 minus 2. So we have following solutions: x square minus x square minus 2x plus 1. So we have already found that a is 1, minus 1, 1 and minus 1. Mod of a alpha is 1. So it could be 1 or minus 1. So we have the roots. Now we can write the second and third equation. Now we write the second and third in the form, I don't know what it means. We'll see. So once we have this, we write second and third. That means this one, okay? So second is x square minus x. So we write this as minus x into 1 minus x. And third one is 1 minus x whole square. So this is x square minus 2x plus 1. So that is 1 minus x whole square. So we can write the general solution in the form minus x to the power p 1 minus x to the power q into x square plus x plus 1 to the power r. So where pqr is in the set of integers. Okay. Now question 209 says that prove that if a polynomial of degree 7 over z is equal to plus minus 1 for 7 different integers, then it is irreducible over z. So suppose p of x, q of x, r of x belong to z, and with p of x is equal to q of x, r of x. Okay. So our polynomial has to be of degree of 7. Now we assume that degree of q is less than or equal to 3, and which is less than degree of r, which is less than degree of p, and degree of p is 7. So that's what we assume. Given that for 7 distinct integers n1 through n7, mod of p and I is equal to 1. Okay. So it is plus minus 1. It is given. So we observe that qx and rx are both polynomials with integer coefficients. Okay. With different integers. 7 different. Okay. Now, once we have that, q and I and r and I would be in the set z for each I. And mod of q and I, r and I will be equal to 1. So q and I is equal to plus minus 1. We see that the value of 1 or minus 1 is taken at least 4 times, but the degree of q of x is at most 3. Thus qx is equal to plus minus 1. Hence p of x is irreducible. So it was a relatively easy problem. Okay. You just have to observe the fact that in this equation, we assumption which we made, that's the tricky one to make. And once you make the observation, rest of it is very easy. Now question 210 says that prove that x minus a1 whole square into x minus a2 whole square up to x minus an whole square plus 1 is irreducible over z. So we consider a function f of x, and we suppose that it factors into two functions g of x into h of x. So we will prove by contradiction. So by Gauss's lemma, we may assume that g and h are monic polynomials with integral coefficients. Let g of x is equal to x to the power k bk minus 1 x to the power k minus 1 up to b0, and h of x is equal to x to the power l c l minus 1 x to the power l minus 1 up to c0. Observe that the polynomial function g and h satisfy g, r, h are greater than 0 for r in, they should be capital R. Such, and that g of ai is equal to h of ai is equal to 1. Okay. Suppose that k less than l, then the polynomial g has the value 1, and then for n distinct values a1 through n, and because it has degree k less than n, then that the polynomial is the constant 1, and the factorization is trivial, which is a contradiction. When k is equal to l is equal to n, f is equal to g square, and then we will have g of x plus x minus a1 up to x minus n, g of x minus, we are basically multiplying. There is something wrong with the sign. Okay. So which is again trivial factorization. In both cases, the assumed non-triviality of factorization leads to contradiction. So basically what we are saying is that we can reduce the given function. So the assumption itself becomes a fact that f is basically irreducible. So with this, we come to the end of this set of problems. I know that the problems have not been explained in great detail. The solutions are not explained in great detail. So if you want, then I can update the PDF to include more detail. I'll explain how we can include certain things. Okay. So let me know in comments if you want to understand these in greater detail. I think of all the videos I have made till date, this is probably the most difficult problem set. Okay, rest of the problem set were relatively easier. So if you are having difficulty, let me know and I'll explain in greater detail. Once we have solved this problem, the rest of the problems I know are easy. Those will be based on straight formulas and assumptions. So 211 onwards, it's going to be easier. Okay. So if you find the video useful and informative, then do not forget to subscribe to the channel if you have not already subscribed. Like the video, share it on social media, share it with your friends so that they can also benefit. And why I'm asking is that because I want more and more people to benefit from these videos. So what I said that I'll show in the end, and I said about it, you go to astapra.org, you click this link, a variable in algebra, and you will get the entire book over here. So this book is complete. I will not add problems very soon. Eventually I'll add problems, but we will see when that happens. So you can download this. It is free of cost. It is under GNU FDL. So basically you don't need to pay anyone, or at least me, to get this. You can print this. You can give it to your friends. There are no restrictions. So make sure you download the PDF and also share it with your friends. Okay, don't be selfish, be a good person, be a generous person, because if I can give it for free, you can also give it for free. So let the goodness spread. Thanks a lot for watching the video. Enjoy.